So, hello students, welcome to this lecture on VLSI design KEC 072. This is lecture number 22. I am Dr. Raman Kapoor, Associate Professor at ABS Engineering College, Ghaziabad. In this lecture, we are going to continue our previous discussion on low power CMOS VLSI design, and we are going to go a bit more into detail and see some actual technique which help us to minimize power dissipation. Okay. So, in the last lecture we have identified some sources where power tends to get consumed or dissipated. Okay. These are your switching power consumption, short circuit power consumption and leakage power consumption. Okay. Switching power is when your circuits switch from 0 to 1 and 1 to 0, and during that whatever power is dissipated, that is a switching power consumption. Short circuit power consumption, as the name suggests, is because of any undesired connections or shorting taking place. Leakage power consumption is because of the reverse saturation current in the reverse bias junctions between the drain source and the substrate. So, you have two p-n junction, one between the source and substrate, another between drain and substrate. When they are reverse biased, some reverse leakage current flows, plus your sub threshold current also contributes to leakage power. Okay. So, these are the sources which you have where or you can say major categories where you can put your power being consumed. Okay. So, when we are talking about low power CMOS design, our aim is to not compromise on the high end performance and still ensure that the power consumption is to a desired level. Okay. For this, it is very important to understand what is the profile of power consumption in the entire area of the chip, what factors or what portion of the integrated circuit are actually resulting in more power dissipation as compared with other areas. Okay. So, if you can identify dominant components of power consumption, you can then focus on those dominant components and actually try and reduce your power consumption. It is like first diagnosing the area where there is a problem and then trying to find a solution or a cure for it. The total power consumption across any integrated circuit can be divided among four major parts. The first is the logic circuit itself. So, this is also the part or the component where your switching power consumption takes place. So, when your logic circuits make some transition, the power gets consumed, plus all the logic circuitry, whatever leakage or short circuiting can take place. Okay. So, all the power consumption which is related to the logic operation of your device or the integrated circuit, this is where one area where power can get consumed. Another is clock generation and distribution. Every digital VLSI circuit will require a clock for its operation, whether synchronous or asynchronous. There can be a global clock, there can be processes which use local clocks also. So, clock generation of clock signals and routing of that clock signals can also consume power. Interconnections, the wires which actually connect from one component to another, that can also result in power getting dissipated. And the off chip driving or your IO circuits, these are your interface with the chip and the outside world and vice versa. So, when you are turning when you are driving inputs or extracting signals from the output, okay, that is where your power can get consumed. So, these are some of the dominant areas where power consumption takes place. Okay. Let us do a small comparison. What you see on the table on your slide, you can see three different VLSI chips, the Intel 80386, the DEC Alpha 21065 and an ASIC cell based application specific integrated circuit. And you can see that they have different feature sizes. Okay. So, the feature size is widely different, the number of logic gates is also different, and the frequency at which they are operating and the supply voltage is also varying. Okay. So, there are three distinctly different integrated circuits, and if you compare the power consumption profile across logic circuits, clock distribution, interconnection, input output drivers, you can see that there is a vast difference. Okay. So, for the first IC you can see that 32% of power gets consumed within logic gates, okay, and this number drastically reduces for other two integrated circuits. The interfacing in cell based ASIC consumes a lot of power, up to 43%, okay, and it is a reasonable number for other two ICs also, right. So, you can see that different ICs, different integrated circuits can exhibit different power dissipation profiles. But one thing which can be observed, that the interfacing, the input output circuit and the clock network generally tend to account for the maximum power dissipation. So, these can be the areas where you can focus on, right. So, this is a bit of an introduction. Let us actually try to understand how you can effectively reduce the power consumption and understand some reasons for it. Okay. In the last lecture we have seen this equation, which is the average switching power dissipation, okay, which depends upon load capacitance, the load being charged, square of supply voltage and the clock frequency. Okay. So, I can say that the power being consumed, the average switching power, is actually proportional to the square of the supply voltage. Okay. And if I can somehow operate my circuit at a reduced power supply, okay, if I can operate my circuit at a reduced power supply, right, I can actually reduce the switching power being consumed, right. This is fairly simple to understand from this equation. So, if I do not touch the clock frequency, if I do not alter the load capacitance, okay, if I keep driving the same load at the same frequency, and if I can reduce the power supply and still maintain the correct operation, this kind of an arrangement is going to reduce my power consumption. Okay. But in most of the engineering problems, and especially CMOS VLSI design, there is always a trade off. Okay. If you try to improve one component, some other parameter might get disturbed. Same happens here. If you reduce the power supply voltage, okay, if you reduce the magnitude of VDD, you can reduce the amount of power consumption, but at the same time you are going to increase your switching delays. Okay. So, this graph here shows you this trend. The parameter on the left hand side or the left half of the y axis is the delay. Okay. So, this shows the trend in delay and this shows the trend in power dissipation. Okay. And the x axis is your supply voltage. So, if you scale down, let us see from right to left, if you scale down your supply voltage, you are going to reduce the amount of power being dissipated, okay, this trend here, which is a good trend. Okay. But at the same time, you are going to increase the amount of delay also. Okay. So, if you try to observe this graph from right to left, you will see that when you scale down on the power supply, if you try to operate your circuit at a reduced power supply, yes, you are going to reduce the average switching power dissipation, okay, or your overall power consumption as well, but at the same time you are going to increase the delays. Okay. But we should not ignore this trend of power consumption at this stage. Maybe we can try and find some kind of a middle ground where your delays do not get very worse and still you can somehow improve your power consumption. Okay. So, the quadratic dependence of the dynamic power on VDD is also influenced by circuit speed. If the circuit is always operated at maximum frequency allowed by its propagation delay, right. So, if I say that there is a x nanosecond amount of worst case propagation delay, right. So, I should have a frequency inverse of that maximum propagation delay. Okay. To find that frequency at which I can operate my circuit and still have reliable operation. Okay. So, the number of switching events per unit time, which is nothing but the operating frequency, okay, it is going to reduce if the propagation delay starts to increase. Okay. If from stage 1 to stage n, the value of delay which it takes for the signal to propagate from input to output, if that starts to increase, my operating frequency will start to reduce. So, the frequency at which I am going to operate this circuit, okay, is going to drop. Right. So, if I reduce power supply, I increase the delays and I reduce my operating frequency. What it basically does is that the power dissipation now becomes more dependent on power supply voltage. Okay. So, now I am in a situation where I do not want to leave this trend, I want to do something with the power supply voltage. If I can reduce that and still keep delays to a useful to a reasonable value, okay, then I can obtain my objective of low power design. Okay. And a possible solution in this direction can be, if in addition to the supply voltage, if I also scale down the threshold voltage. Okay. The threshold voltage, as we know by now very clearly, for an N MOSFET it is that value at the gate potential gate electrode which must be exceeded for it to turn on. Okay. And for a PMOS it is of opposite polarity. So, it should be a value which goes more negative than the threshold voltage. So, the PMOS turns on. Okay. So, if I also scale down my threshold voltage in addition to my supply voltage, the negative effects of voltage scaling on delay can be compensated. How? Because if the threshold voltage is less, the switching becomes faster. Okay. So, the reduction in operating frequency when delay starts to increase, if I am reducing my operating frequency, okay, if I start to operate that device at a fast switching speed via lower threshold voltage, it is going to turn off, on, off, on, off at a fast pace. Okay. So, the negative effect of delay on operating frequency can be compensated. Right. So, going in this direction, if you observe this graph, again the x axis is the supply voltage, the y axis is nothing but delay. Right. So, this graph does not show the power, it only shows the effect of the threshold voltage on the delay value as your power supply is scaled down. Okay. So, if I move again, so if you see the x axis from right to left, if I reduce my power supply voltage and if I reduce my threshold voltage, at any given point of time for any value of supply voltage, okay, if I reduce the threshold voltage, the normalized value of delay also goes down. Experimentally it has been found that if you reduce the threshold voltage, now I am talking about NMOS here, okay, because I mentioned a positive value of threshold voltage, I am talking about an N type MOSFET. If I reduce the threshold voltage from 0.8 to 0.2 volt, it improves the delay at VDD equal to 2 volt by a factor of 2. Okay. So, this is a this you can, instead of focusing on the numbers, try to focus on the trend, right, because there are other parameters also like the device dimensions, geometry, architecture, right, and other some electrical parameters are also there, but the trend remains the same. If you reduce the threshold voltage, you are going to improve the value of delay, and if you improve the value of delay, your operating frequency is going to improve, and at the same time what this helps you is, it can help you in reducing the power consumption as you scale down your power supply. So, now in this kind of an arrangement, you can safely or in a wider range, you can reduce your power supply voltage, scale down, reduce the power consumption, and at the same time do not cause large increase in delays. So, your operating frequency also remains in reasonable value, right. So, but then again there is another catch to it. If you use low threshold voltage transistors, yes, switching improves, but then there is problem about noise margin, how much noise you can apply at the input before your output changes its value, okay, and the sub threshold condition. Now, when you reduce the threshold voltage, in some cases an increased noise signal can also turn your transistor on. So, smaller threshold voltage leads to smaller noise margin and it greatly increases the probability of sub threshold conduction. Now, MOSFET being a switch in a digital circuit, you do not want this switch to be turning on when it is supposed to be off. Okay. So, we tried to reduce the threshold voltage to improve delay, so that we can exploit the advantage of voltage scaling on power dissipation, but now we are faced with another problem of sub threshold conduction and noise immunity. Right. For this, there are different techniques, the two techniques being variable threshold CMOS or VT CMOS and multiple threshold CMOS or MT CMOS. Okay. These two techniques actually help you to design your devices in such a way that you can make use of both. You can reduce, you can scale down on your power supply voltage, reduce the power consumption, have reasonable values of delay, okay. Do not increase the delays by much, and at the same time control your sub threshold conduction. Before we discuss these two techniques, let us study a very important concept which is known as the body effect in MOSFETs. Okay. So, it is known as body effect. Okay. Most of us consider NMOS or any MOSFET as a 3-terminal device. Okay. Let us take the example of an N channel MOSFET. Okay. So, you have a P type substrate, you have a body electrode, you have source, you have drain, and then you have a gate oxide, okay, and then you have a gate electrode. Okay. Generally, you are going to short these two together to convert to a single terminal, and then this becomes your ground or your reference. Okay. So, all the voltages are compared with respect to this terminal only. Whatever you apply at drain and gate, you measure with respect to this. So, now it is a 3-terminal device. What if we do not short these, instead I apply some voltage here. Okay. Let us call it VSB. Okay. So, this is your body electrode. Okay. In this case, what is going to happen? So, see, I have connected the negative terminal to the body and the positive terminal to the source. In this case, this negative polarity on the body or on the substrate is going to attract a lot of holes towards it. The P type substrate has a lot of holes in majority. So, it attracts a lot of holes. What it leaves behind is some negative acceptor ions. Okay. Some negative acceptor ions are left behind. So, this depletion region between source and substrate, it tends to expand, the width increases for this depletion region. The magnitude or the intensity of reverse bias between the source and the substrate tends to increase, and when this reverse bias increases, the conduction between source and drain or the flow of electrons between source and drain, which produces current, that goes down. This is analogous to increasing the threshold voltage. How? Because now for the same amount of current, you will have to apply a higher voltage at the gate. Okay. So, if VSB was 0, if source and body was shorted together, in that case you would just simply apply some threshold at the gate and produce current. In this case now, you will have to apply a higher voltage for the same level of current. This basically means that without making a lot of changes in the geometry or the doping concentrations, you have effectively increased the threshold voltage. Now, you can design transistors with lower threshold, okay, with lower delays, better power consumption, and still control the sub threshold current by controlling this body bias. Okay. So, this using this concept in mind, we have two techniques, one is VT CMOS, another is MT CMOS. Both these techniques exploit this body effect. We design a circuit which helps you to toggle or to tune the threshold voltage of MOSFETs in such a way that in one particular case it works as a normal circuit, in another case it tends to control the sub threshold conduction. Okay. So, let us discuss these techniques, VT CMOS or variable threshold CMOS as we know it. Here you take this example of an inverter. In addition, we have got a substrate bias control circuit. Okay. we have defined two modes, active and standby. Active and standby. Active basically means when that transistor is on, and standby means when that transistor is off. Okay. So, when this NMOS is in active mode, you have nothing, you have 0 voltage applied here. So, there is no body effect, okay, things work like normal. But when this NMOS goes in standby mode, then some negative voltage is applied across the body. It tends to increase the threshold, effective threshold voltage, and discharging through this NMOS is avoided. Okay. So, while we want the correct operation during active mode, we operate in a normal way, right, and in the standby mode or in the sub threshold mode, when the transistor is supposed to be off, we effectively increase its threshold voltage, and when its threshold voltage is exceeded, there are more chances of sub threshold current being reduced. Okay. Same happens to this PMOS. When it is in active mode, you have a some positive voltage, okay, and in the standby mode this positive voltage is increased. Okay. So, because in NMOS a negative voltage at the substrate increases the threshold voltage, for the complementary nature a higher positive voltage across the substrate is going to increase the threshold of the PMOS. Okay. So, in either way, whenever either PMOS or NMOS are in standby mode, its threshold voltage is effectively increased, so that sub threshold conduction can be reduced. So, now we have got the best of almost everything. You can scale down your power supply, you can improve the power consumption, right. Since you are using low threshold voltage devices here, you can reduce the delay also. So, your operating frequency is maintained, and at the same time you are using a substrate bias control circuit. Whenever your low voltage, low threshold voltage devices undergo standby mode, when they are not supposed to be working or when they are not supposed to be used, in that case the substrate bias effectively increases its threshold voltage. So, even if there is noise in the circuit, even if there is some parasitic effect, those transistors which are in standby mode do not turn on. So, sub threshold conduction is also avoided. Okay. This technique is variable threshold CMOS or VT CMOS. Another technique which more or less uses the same mechanism is multiple threshold CMOS or MT CMOS. As the name suggests, here you use transistors with different values of VT. Okay. So, you are going to have a transistor here PMOS with high threshold voltage and NMOS or with high threshold voltage. Okay. The gate electrodes are connected to a standby signal which is complementary. So, when this standby is 0, this is 1, when this is 1, this is 0. Okay. And then you have your normal CMOS logic in the middle using low threshold voltage transistor. So, all the circuit operation or all the logic operation is actually implemented by low threshold voltage circuits only or low threshold voltage devices only. Since you are using low threshold voltage for your circuit operation, you can reduce delay, you have the liberty of scaling down your power supply, which helps you to design or achieve your low power VLSI design circuit. Okay. At the same time, you control your sub threshold currents. Okay. So, in the standby mode, when this is off or this is off, okay, or when we say standby mode, we mean the standby mode here. When your low VT circuit or low VT device circuit is not performing anything, okay, if there is any charge loss or if there is any circuit or any sub threshold current flowing through these devices, that current cannot get connected to the power supply or that current cannot discharge to the ground, because they are sort of shielded by these high threshold voltage circuits. Okay. So, this does not turn on, this does not turn on during standby. So, whatever leakage or sub threshold conduction may be happening here, that gets confined to this logic only. Okay. So, this is how you control your sub threshold conduction while maintaining the target of low power dissipation. Okay. So, as it is written here, the low threshold voltage transistor, they are used to obtain fast switching. Okay. Lower the threshold voltage, easier it is to turn off and on. So, high switching speed, whereas your high threshold voltage transistor are going to avoid any kind of leakage. Okay. So, your logic circuit, actual useful logic circuit cannot charge up to VDD, it cannot discharge to ground, because it is prevented by the high threshold voltage PMOS and NMOS standby transistors. Okay. So, this is empty CMOS technique. As compared to VT CMOS, empty CMOS occupies lesser area, okay, and it is easier to implement. Okay. So, it is generally preferred over VT CMOS. Okay. So, we have considered two CMOS design techniques which exploit the body effect, which is the tuning of the threshold voltage, okay, via body potential. Okay. So, whatever you apply at the substrate with respect to the source, if it is more negative for an NMOS, it increases the threshold voltage. If it is more positive for a PMOS, it increases the threshold voltage. So, without making any design changes, you have actually influenced the threshold voltage of the device. Okay. So, these techniques actually help you, allow you to use low threshold voltage circuits, okay, make use of their low threshold voltage on delay and power, and at the same time control the sub threshold conduction. Okay. And this is one example of a D latch circuit, which you can see. So, this is your low VT section. Okay. This is a simple D latch circuit. We have, when we did sequential CMOS design, we have seen how D latch works and how it can be implemented in CMOS. Okay. In addition, you have these PMOS here connected to standby signal, NMOS here, okay, and then this is a bistable latch element. So, whatever comes out gets latched into this circuit. Okay. So, you can see the shaded region is a normal circuit, but you use low threshold voltage devices, and you use high threshold voltage devices for reducing leakage in standby mode. Okay. In addition to these, there are two more approaches. These are known as parallelism and pipelining. Pipelining in one form or the other we have already seen in sequential circuit design. Another way is parallelism. Okay. Parallel connection or parallel CMOS design is what? Where you have a single functional unit, but you divide it in n parallel unit, so that each can operate at 1 by n of the overall frequency. Okay. This is known as parallelism or parallel technique. For its operation, you use a multiplexer. It selects between different results. The voltage can be scaled down. So, your quadratic relation between power and voltage, that can be exploited here. Okay. The only negative aspect of parallelism is that it doubles the area. Okay. Similarly, you can use n stage pipelined circuit. Okay. If you remember, we did pipelining in sequential circuit design, where you would insert registers deliberately, so that after a certain number of clock cycles you have actually reached an advanced stage of operation. Okay. So, some intermediate stages are already done. You do not have to wait for the entire clock cycle for one operation to take place, and by the time some clock cycles have happened, you are actually already at a stage where some of the preliminary operations are already performed. Okay. So, parallelism is when you divide a functional unit in n parallel blocks, where the result is selected via multiplexer. Pipelining is where you insert registers between input and output, okay, and they are in a clock cycle. Okay. The only negative aspect here is that you introduce more registers. So, this diagram basically here tells you, the first diagram shows you a normal operation, two logic blocks A and B. So, you reach from input to output. Okay. This is parallelism, where you divide into parallel. So, this stage, they are working in parallel, they are driven by a multiplexer. So, one of them can be selected at a time. Okay. So, if you have two parallel lines being operated simultaneously, you can use a multiplexer to select either one of these, the output of either one of these. So, suppose you have an output here, one output here, another, one of them can be selected via the selection line, and that goes to the output. This is parallelism. Okay. So, you can see that a lot of area is being consumed here. Another is pipelining, where you insert register between multiple stages. So, whatever is done here, the output of A is stored here in this register, and then it is transferred to B in another clock cycle. But at the same time, in the same clock cycle, the output of A is again updated. So, you do not have to wait for entire, say if you have n stages, you do not have to wait for n number of clock cycles. By the time n clock cycles elapse, you already have updated the data of register of circuit A. Okay. So, by the time the final output reaches here, the output for next stage might already have reached here. Okay. In the normal approach, it will still be here. So, this is the approach of pipelining. Okay. These are also another two techniques which help you to basically reduce your overall power consumption and produce low power VLSI design. Okay. So, with this we come to the end of today's lecture. We have completed a very important topic where you utilize the effect of power supply voltage on the power consumption. Okay. So, there is a quadratic relationship between power supply and power dissipation. When you scale down power supply, you reduce power consumption, but you increase delays. Increasing delays affect your operating frequency. To counter that, you reduce the threshold voltage, but it increases sub threshold conduction, and to counter that you can use empty CMOS or VT CMOS. Okay. So, with that we end today's lecture. Thank you.